Hello everyone, and welcome back. Today we're going to be continuing our exploration of real valued functions and discuss differential equations and some of the important things that you definitely should know about differential equations that you probably learned before, but we're going to be looking at a couple things from the theoretical perspective instead today. So, we're just going to be focused on the first order differential equation and also the first order linear differential equation, and briefly mention a couple little side notes on higher order differential equations as well. But practically, once you have all the theory for first order down, you can build nth order differential equation stuff and also systems of differential equations as pretty easy corollaries just from these principles, together with linear algebra. So, what we're going to be looking at is the derivative of some differentiable function y of a single variable x, and let's assume that this is equal to some implicit representation of the independent variable x and also itself. And let's assume that we have some initial condition y of x is 0 is equal to y0. And let's assume that these functions y, f, x0, y0 are all well defined. So what is the goal of differential equations? So the goal is to solve this ODE on as much of the domain of real numbers at x0 and after as possible. But in particular, all we really need to do is to solve this ODE on some neighborhood of some size delta around x0, in particular on the right of x0 or even before, depending on how you're going to approximate the solution. And here, this delta is an arbitrarily small positive number. So as long as we can solve around this initial condition value x0, then all is going to be well. And then it can move along in that domain and then solve in a neighborhood around that and move on forward, do a neighborhood around that, and so on. So the main theorem that guides the existence and uniqueness of solutions for first order initial value problems is the following. And this is usually referred to as the Picard or the Picard-Lindelof theorem. And this says the following. So the initial value problem given by y prime of x is equal to fxy with initial condition yx0 is equal to y0 has a unique solution. So we have existence and uniqueness, so this is sometimes also referred to as the existence and uniqueness theorem for first order ODEs, if in particular it has a exist and unique solution on the interval some neighborhood around x0 if the following two conditions are met. The first condition is that this function f on the right hand side of the ODE is continuous on the domain associated to x, in particular some domain of x0. And a second condition, f must be Lipschitz continuous in the y variable, in particular some neighborhood, let's say epsilon of y0. And here delta and epsilon are arbitrarily small but positive numbers. So if we think about what we're looking at here, so practically what we have is some initial condition. Let's assume we have x0 and y0, and we're trying to find the solution that sort of, satisfies this particular relation. So let's just do it in dotted blue. So as long as this function f, which describes the rate of change, because f represents the derivative of y at a bunch of different points, x, y, and r2, then as long as the curve satisfies some properties, so it has to be continuous in this region, so this is practically your neighborhood of x, and it also has to be Lipschitz continuous in this region here, right? So practically what we have here is a little rectangle around our solution, right? So as long as it's continuous in the x direction and Lipschitz continuous in the y direction, then we should be able to find the unique solution of this curve at that point and some local two-dimensional neighborhood around that point. And as long as it satisfies those two conditions, then by the Picard-Lindelof theorem, we have our unique solution. So before we give a sketch of the proof of this, let's just go through a couple examples of differential equations to sort of see if they have a unique solution at all. So let's start off with a very easy one that you probably already know how to solve. And that's y prime is equal to y plus e to the x with the initial condition y of 1 is equal to 3. So the first thing that we need to label is our f. So our f xy, in this case, is going to be y plus e to the x. So is this continuous in the x variable near x is equal to 1? So all we really need to analyze in terms of x is the following function. So g of x is equal to some constant, because y is a constant as far as x is concerned, plus e to the x. And this is just an exponential function, and we clearly see that g is continuous in some neighborhood of radius delta around x is equal to 1, so that's not a big deal. And then we can look at another function, h of x, which is going to be equal to y plus some other constant, let's call it just d to represent e to the x, because we're just looking at y, not x. And we need this to be Lipschitz continuous in a neighborhood of y. So what does it mean to be Lipschitz continuous? Well, that means that the derivative is bounded. And if you don't remember that little result, remember what it means to be Lipschitz continuous. So if you pick any 2 points in the domain, let's call them x and let's call them y, so h of x and h of y, then that means there must exist some constant k, which is strictly greater than 0, such that k times x minus y satisfies this result. So if you look at this and rearrange this, practically what you have here is h of x minus h of y all over x minus y is less than or equal to k. And that's just the central average difference of your first order derivative. So as long as your derivative is bounded, then we have that this is definitely Lipschitz continuous in that region, right? As long as x and y belong to some neighborhood of y0. So if we take the partial derivative of h with respect to y, that's obviously going to be 1, and 1 obviously is bounded, right? Because 1 is less than or equal to 1 for all y and r. Moreover, all y in some neighborhood of y0. And what was our y0? y0 was equal to 3 for our example, right? So it's Lipschitz continuous in a neighborhood of y0 because the derivative is bounded in that interval, moreover on all of r. Therefore, since the function f is continuous in x and Lipschitz continuous in y, that means what? So that means there exists a unique solution to the ODE in the Cartesian product n delta x0 Cartesian product with n epsilon y0. So in that little rectangle we have a unique solution. In particular, you should be able to find it actually. So keep in mind we had y prime is equal to y plus e to the x, where y of 1 is equal to 3. Using your method of integrating factors, if you want to sort of, practice this before we get into a brief discussion on integrating factors, you should be able to show that the exact solution, which I'm going to call yp, is actually equal to e to the x times x plus c, where that c is actually equal to 3 divided by e minus 1. So that's a nice little exercise to practice your basic differential equations in case you're interested. Let's look at another example to sort of see if this differential equation has a unique solution in the neighborhood around our initial condition. So we have y prime is equal to x times the square root of the absolute value of y. So what do we need to show? So this is going to be our f of x, so that's going to be x times the square root of the absolute value of y. So we need to make sure that it's continuous in x. So if it's continuous in x, that means we're going to have, so the square root of absolute value of y is just a number, so I'm just going to call it ax, where a is a positive number. It could be 0 as long as we know. So a is greater than or equal to 0. So we have g of x is equal to a of x, which is obviously a linear function, and obviously we know that this linear function is going to be continuous and also differentiable, but it's going to be continuous in the neighborhood around x is equal to 5. Moreover, it's continuous on all of r, right? So the first property for existence and uniqueness is satisfied. Now we're going to define a new function, let's call it h of y, and that's going to be equal to, so x is a constant as far as we're concerned, so we're going to have a times the square root of the absolute value of y. And we need to make sure that this is Lipschitz continuous in our region. So what we're going to do is we're going to take the partial derivative with respect to y of h of y, and that's going to give us a divided by 2 square roots of absolute value of y, and then we need to differentiate the absolute value of y, so that's going to be equal to the absolute value of y over y. So we have 1 absolute value of y and 1/2 absolute value of y on the bottom. So we can write this instead as a times the square root of the absolute value of y on top all over 2y. So we need to make sure that this function is bounded near our initial condition. And keep in mind our initial condition was y5 is equal to 0. So 0 is my point of interest. So is this bounded near y0? So if we get close to 0, notice that we do have a rational singularity there. Therefore, we do have some issues, right? So this is not continuous, it's unbounded. So it's unbounded near y is equal to 0. That means that this function f is not Lipschitz continuous in y, right? So what does that mean? That means we do not have no unique solution to the ODE in the region n delta of 5 Cartesian product within epsilon of 0. Right? Now, you could have a unique solution elsewhere, but you won't have a unique solution or even an existing solution at this point. Now, the proof of the Picard-Lindelof theorem, at least one of the more traditional proofs at least, requires a bit of machinery similar to the bisection method, which is used to prove the immediate value theorem commonly. And this method, called the Picard's iteration method, can also be used to construct solutions of differential equations, especially if you don't know any clever calculus tricks to solve them. And it begins by defining a sequence of functions of x, right? So we're going to define the initial condition to be equal to the y initial condition y0, and we're going to define the rest recursively. So we're going to have 5n plus 1 of x is equal to the initial condition y0. The integral is going to range from x0, the initial condition of x, to our variable x, and then our function f evaluated at t, the last iteration of our sequence, and then we're going to integrate with respect to time, right? So the claim, at least for the time being, is that this sequence obviously converges, and the sequence of these functions is going to be equal to y, our unique solution. Obviously, if this solution does converge to the correct thing, limits are unique, so uniqueness practically falls immediately from our properties of limits of sequences, right? So let's do a quick example to sort of see how this iteration works, and then we'll provide a sketch of the proof of the Picard-Lindelof theorem. So let's look at a very basic differential equation to sort of guide us through this territory. Let's look at y prime is equal to x plus y with the initial condition of y is 0 is equal to 0. So we'll make the numbers really, really nice. So what is phi 0 going to be equal to? So phi 0 is going to be equal to the initial condition of y. So it's going to be equal to 0. And then phi 1 will be equal to, again, y0 plus the integral from x0, which is 0 to x, and then f, which is that side, evaluated at t, and then phi 0 of t dt. So that means this is going to be equal to the integral from 0 to x of t plus phi 0 of t, which is going to be equal to 0, integrate with respect to time, and that's going to be equal to 1/2 x squared. All right, so that's going to be phi of 1. And then we're going to repeat this process. So phi of 2 will be equal to what? So it's going to be 0 plus the integral from 0 to x of t plus phi of 1 of t dt. So that's going to be equal to what? So that's going to be equal to the integral from 0 to x of t plus 1/2 t squared dt. So we're going to plug in x after we anti-differentiate, so that's going to be equal to 1/2 t squared, plus that 2 is going to come down, and after it turns into a 3, so we're going to have 3 factorial on the bottom, so I'm going to write that as 3 factorial. I'll write that as 2 factorial also. And then that's going to be equal to t cubed, and obviously we need to send t to x, t to 0, and that's going to give us your 1/2, 1 over 2 factorial, x squared, and then 1 over 3 factorial, x cubed. Right? So the trick or the important part about the Picard-Lindelof theorem, if you want an exact solution, is to be able to pick up patterns extremely, extremely quickly. So you might be able to see the pattern now. So what do you think phi 3 would be? So if you follow the same procedure, you should be able to see that this is going to be equal to 1/2 x squared, or 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed, plus 1 over 4 factorial x to the power of 4. Once you get there, hopefully this pattern is consistent, and then you can use mathematical induction to build the general case. So phi n of x, at least it looks like, notice that we have 3 and 4 is the highest exponent here. So we're going to be summing from k is equal to 2 to m plus 1 of x to the power of k over k factorial. So it's part of the series of e to the power of x. So what is the limit as n goes to infinity of this sequence of functions? So that's obviously going to be equal to the sum from k is equal to 0 to infinity of x to the k over k factorial minus, notice I've added 0 and 1 here sneakily, so it's going to be the sum from k is equal to 0 to 1 of x to the k over k factorial. So that would be the limit, provided that we prove this statement with mathematical induction. So we know that that's going to be equal to e to the x, and over here we just have x plus 1. So we can write this as e to the x minus 1, and you should be able to show that this is indeed the solution to the differential equation I presented before. So let's do a quick sketch of how the proof of the Picard-Lindelof theorem actually goes, right? So provided that f is continuous in x, and also that f is Lipschitz continuous in y. So if it's Lipschitz continuous in y, that means the absolute value of fxy1 minus fxy2 must be less than or equal to m times the absolute value of y1 minus y2. And that has to be true for some m in the set of real numbers strictly bigger than 0. So one should be able to show, and this I'll leave for you, that there exists a c in between 0 and 1, such that the following thing is true, right? So let's look at the iteration between our iterates, our phi's. So in particular, phi m plus 2x minus phi m plus 1x. So this obviously, if we just use our definitions, is going to be equal to y0 plus the integral from x0 to x of f of t phi m plus 1 of t dt, so that's the first, minus y0 plus the integral from x0 to x of f of t phi n of t dt. Notice that these y0s will eliminate, and that negative sign will subtract. And notice that these integrals are of the same exact boundary. So we can write this as the absolute value of the integral from x0 to x of, and we can do this as f of t phi m plus 1 of t dt minus f of t phi n of t dt. And that's going to be our integral. So using the properties of continuity and Lipschitz continuity, after some nice integral tricks as well, you should be able to show that this is going to be less than or equal to our number c, which is between 0 and 1, times the difference between these elements here, which is going to be equal to phi m plus 1 of t minus phi n of t. And that's going to give you phi m plus 2 of t, or x, let's say, minus phi of m plus 1 of x. So if c belongs to 0 to 1, that means that the sequence phi n is a contractive sequence. And if phi n is contractive, that means it's Cauchy, and if it is Cauchy, that means it converges. And since it converges, that means we have existence, and due to the uniqueness of limits for convergent sequences, we also have uniqueness, right? So that will give you practically the proof of the Picard-Lindelof theorem once you are able to fill in these happy little details in between these inequalities. If you've taken differential equations already, you probably know this result quite well. And this gives you a theorem that guarantees the existence of an integrating factor for first-order linear differential equations. And there is a more advanced one for exact and non-exact differential equations that we won't present here, but definitely you should be aware of it. But it requires a little bit of PDEs in order to thoroughly investigate. And this theorem says the following. So let's assume that alpha is a Riemann integrable function on R, and let's assume that the product of the function beta with the exponential of the antiderivative of alpha, let's assume that that function is also a Riemann integrable on R. If both of these things are true, then there always exists a function that is differentiable on R, such that fy prime plus afy equals bf, where this a should be alpha and b should be beta. This is a separable ordinary differential equation that can be solved via integration, provided that the solution to this differential equation y is not identically equal to 0 on the set of real numbers. So let's see if we can go ahead and prove the existence, not necessarily uniqueness, but it is unique up to scalars, of an integrating factor. That's what this f is called. So what are we going to do? So let's suppose that we have our differential equation y prime plus alpha xy is equal to beta x. So this is our first order linear, potentially inhomogeneous differential equation. And let's suppose that f is a function such that the derivative of fy is equal to fy prime plus a fy. So if this function is one that satisfies this criteria, then that means if we use the product rule on the left-hand side, we're going to have fy prime plus f prime y will be equal to the right-hand side, so fy prime plus alpha fy. So once we have this, notice that we do have some commonalities in this expression, in particular this fy prime, and those can cancel, and this is just going to give us f prime y is equal to alpha fy. And keep in mind, we're assuming that y is not identically equal to 0, so we can cancel these terms out. And then we're just going to have f prime is equal to alpha f, which is just a differential equation in terms of alpha. So if we write that in differential form, we can write that as the derivative of f with respect to x is equal to alpha of x times f of x. And we can move our f's to the left-hand side and our differential of x to the right-hand side. So we're going to have the differential of f divided by f is going to be equal to alpha of x dx. So if we integrate both sides of this equation, the integral of 1 over f with respect to f obviously is going to be equal to the natural log of f of x, and that's going to be equal to the antiderivative of alpha x. So this is where the Riemann integrability of alpha comes into the picture. And then we're going to have the exponential of both sides. So we're going to have f of x is equal to e to the integral of alpha x dx plus some constant c. And that's going to give us our function f. And I'm going to call e to the c equal to k. So we're going to have k e to the integral of alpha x dx, where k is some positive real valued constant. Right? So that's what our integrating factor is. And if you have that, then what exactly are you going to have? So how can we justify the separability of our original differential equation? So we're going to have y prime plus alpha y is equal to beta, and then we're going to multiply both sides of this equation by f. So we're going to have y prime f plus alpha fy is equal to beta f. So on the left-hand side, you should be able to verify that the derivative of y times this scary little function is actually equal to that left-hand side, and that's going to give us beta f. And then we can integrate both sides. Once we multiply both sides by a differential of x, that's going to give us what? So that's going to give us y f will be equal to the integral of beta times f. But what is f? Well, f is a scalar multiple of e to the integral of alpha x dx, and that's with respect to, again, you could call it dx. So this is where the Riemann integrability of beta e antiderivative of alpha comes into the play, because then we can solve this differential equation because it is separable for y. So we're going to have that y is equal to 1 divided by f of x times some constant c plus that scalar multiple of our integrating factor times the integral of beta of x e to the integral of alpha of x dx dx. And that is our general solution to our original first order linear potentially inhomogeneous differential equation. So let's actually do a little numerical example to sort of see how this works, just in case you have not formally taken a differential equations course in a while, or maybe you need a little bit of practice. So let's assume that we have y prime is equal to sine of x minus y. You should be able to show that this differential equation will have a unique solution regardless of the initial condition for which we superimpose. So let's just find the general solution. So I can rearrange this as y prime plus y is equal to the sine of x. And then what I can do is I can find our integrating factor because we know it exists. So this is going to be equal to e to the integral of the function in front of y, which is 1 dx. So that's going to be equal to e to the x. So that's going to give us y prime e to the x plus e to the xy equals e to the x sine x. And we already know that this should be a backwards product rule in disguise every single time. So that's going to be equal to the derivative with respect to x of our solution times our integrating factor, and that's going to be equal to e to the x sine of x. Multiply both sides by a differential of x and then integrate. So we're integrating 1 with respect to that function. That's obviously going to be that function y times e to the x, and that's going to be equal to some constant plus the antiderivative of e to the x sine of x dx. Now, this integral on the right-hand side is a very famous one. You can do it by integration by parts twice, or you can do some clever exponential tricks as well in order to evaluate it. But once you actually do evaluate it, you can find that's going to be y e to the x, and then c plus 1/2 sine of x minus cosine of x. Then you can multiply both sides by the inverse of e to the x. That's never equal to 0. And then you can find that the exact solution, or the general solution, to that original differential equation is just equal to 1/2 of, oh, I also forgot my e to the x there. Let's not forget that. So the e to the x's will cancel there, which is actually quite nice. And then we're going to have sine of x minus cosine of x plus c times e to the minus x. Notice that the end behavior as x goes to infinity is actually going to kill that term out. So regardless of that initial condition, which c depends on entirely, the solutions, all of them, are going to behave just like this function here, right? And that's practically, where you get into your equilibrium solutions and all your phase portraits and all that. But we're not going to get into that here, but that is definitely a wonderful discussion to investigate if you haven't already done so. Now let us consider what it means for a function to be of exponential order. So consider function f. So we say it is of exponential order if there exist two positive real numbers, omega and m, such that the absolute value of f of t, that is the function is bounded, by this function, m, the constant, times e to the omega, a constant, times t, where t ranges from 0 to infinity, and all t must satisfy this definition. So let's explore this definition a little bit and look at a couple alternative ways of thinking about it. So if this is true, we can also write this as the absolute value of f of t times e to the minus omega t must be less than or equal to some number m. So you can think of this as a function and it being bounded by a constant. You could also look at this as a quotient and look at this as the absolute value of f of t over e to the positive omega t, and that being bounded. Since we have an inequality, we can also apply limits. So we can say that the limit as t goes to infinity of the absolute value of f of t over e to the omega t must also be less than or equal to m. Obviously, if you have a function, such as a constant on top, that limit will go to 0. If you have a polynomial, again, that limit will go to 0. And 0 is always less than or equal to a positive constant m. Right? So if the limit of this quotient via, say, L'Hopital's rule or some dominated convergence theorems that you might have converges to 0, or a constant that's positive, then you can always verify that this function f is of exponential order. Now, why do we care about this idea? So this is where the next theorem comes into play. So if f is of exponential order, then this transform, which I'm going to represent as fancy L, of f of t, which is going to be an integral transform, the integral from 0 to infinity, of f of t times e to the minus omega t dt exists for all omega greater than 0. And we call this the Laplace transform of f. Obviously, our integral is ranging over t, and therefore this is going to result into a function of omega, which I'm going to denote as capital F. Okay, so a function has a Laplace transform as long as it is of exponential order. And the proof of this practically comes directly from the absolute convergence test for either series or integrals. Either one would suffice. So the first question I have for you is the following. Is polynomials of the form f of t is equal to t to the n of exponential order? So if we consider the limit as t goes to infinity of t to the power of n over e to the omega t, is this equal to 0? Well, we already know that exponentials and polynomials are infinitely many times differentiable, so we can apply the L'Hopital's rule to this because we have infinity over infinity n times, right? So if we apply L'Hopital's rule n times, we're going to have the limit as t goes to infinity of n factorial all over omega to the power of n e to the omega t. Now we have a constant on the top and a monotonically increasing function on the bottom, so that trivially goes to 0, and obviously that's going to be equal to less than or equal to m for any m, and obviously for any positive omega number. So that means that the Laplace transform of Tn exists. Okay. Now, just because it exists doesn't necessarily mean finding it will always be easy, but in this case, we actually have a nice derivation. So what is the Laplace transform of t to the n? So by definition, that's going to be equal to the integral from 0 to infinity of t to the n e to the minus omega t dt. So we're going to be using a substitution. In particular, I'm going to be targeting that omega t. So we're going to let u be equal to omega t. So du be equal to omega times dt. Obviously, if u is equal to omega t, that means t is equal to u over omega as well. And since omega is a positive number, our range, 0 to infinity for t, will also map to the same exact interval, 0 to infinity for u. So once we do the substitution, this is going to give us the integral from 0 to infinity of t, which is u over omega to the power of m, e to the minus u, and dt is du over omega. So once we have this, now we just need to do some algebra on this object. So notice that we have n omegas on the bottom, and we also have an omega there. So we can write this as 1 over omega to the power of m plus 1 times the integral from 0 to infinity of u to the power of n e to the minus u du. And I can also write this integral as the integral from 0 to infinity of u to the n plus 1 minus 1 e to the minus u du. The only reason I'm writing it this way, because that's just a variable, say u to the x minus 1 e to the minus u du, and that's just a gamma function evaluated at n plus 1. So that means the Laplace transform of t to the power of n is just going to be equal to gamma of n plus 1 all over omega to the power n plus 1. Right? And that's the proof for the Laplace transform of t to the power of n. And another useful one is the Laplace transform of e to the AT, where a is a real number. And you should be able to show that this is equal to 1 over omega minus a using similar tricks using the definition of a Laplace transform. Now, another important identity that you definitely should know in regards to the differential equation, now let's suppose that f is differentiable on R or a useful subset of it. And let's assume that f prime is of exponential order, implying that the derivative of f has a Laplace transform. So what is the Laplace transform of f prime of t? And do we even have to find f prime of t in order to find its Laplace transform? And that's an interesting question. So by definition, that's going to be equal to the integral from 0 to infinity of f prime of t e to the minus omega t dt. So we're going to be using integration by parts here. We're going to be letting u be equal to our e to the minus omega t, forcing the differential of u to be equal to minus omega e to the minus omega t, since our derivative was with respect to t. And then the rest of it is going to be equal to f prime of t dt. So that means v is going to be equal to f of t. So keep in mind this is an integral from 0 to infinity, so do not forget your limits. So this is going to be equal to uv, so e minus omega t, f of t, and this is going to range from infinity to 0, minus the integral from 0 to infinity v du. So v is going to be equal to f of t, and du is going to be equal to e to the minus omega t dt, with a minus omega in the front. So once we have this, we have what? So when we go to infinity, notice that that exponential is going to go to 0, and obviously that's true because f is of exponential order. So it's technically in some sense bounded. So that definitely is going to go to 0. And that bottom limit shouldn't say infinity, it should say 0. As t goes to 0, that term goes to 1, and then we're just going to go to f of 0. So we're going to have 0 minus f of 0. And then over here we have omega times the, what is that? Well, that's just the Laplace transform of f of t. So that means the Laplace transform of the derivative of a function can be represented in terms of its Laplace transform of its antiderivative. In particular, omega times the Laplace transform of the original minus f of 0. Right? And that's a very, very useful tool. So let's actually look at an application of where we can actually use this to solve differential equations. So suppose that we want to solve y prime plus 3y is equal to x. Now, just as a heads up, if you're not familiar with Laplace transforms, dealing with linear differential equations, super easy, super straightforward for Laplace transforms. Now, if you have like y squared, that definitely increases the difficulty exponentially. Also, if you multiply your y prime, your y double prime by functions of x, that also makes things slightly more difficult, but not super impossible. But nonlinear equations definitely pose an exponential increase in difficulty for Laplace. So only usually use Laplace transforms if you want to analyze linear differential equations, which this is an example of. Let's also introduce an initial condition, in particular y of 0 is equal to 1. So what I'm going to do is I'm going to apply the Laplace transform to both sides of this equation. So we're going to have the Laplace transform of y prime plus 3y equals the Laplace transform of x. All right? One should be able to show that linear Laplace transforms are linear operators, so we can distribute over addition, and constants can factor out of the Laplace transform because it's just an integral, and integrals are linear. So once we have that, we're going to have the Laplace transform of y prime plus 3 times the Laplace transform of y, and that's going to be equal to the Laplace transform of x. So once we have this, now we can use our identities for Laplace transforms. So the Laplace transform of y prime can be written in terms of the Laplace transform of y as omega times the Laplace transform of y minus y of 0. And then over here we have 3 times the Laplace transform of y. And the Laplace transform of x, as we already know, keep in mind that's just 1. So that's just going to be equal to gamma 2 all over omega to the power of 2. Right? And keep in mind gamma of 2 is just 1 factorial, which is just going to be equal to 1. So once we have that, notice that I have a Laplace transform and a Laplace transform there, and I know that y0 was chosen to be equal to 1. So I'm just going to move that to the right-hand side. So I'm going to have omega plus 3 times the Laplace transform of y is going to be equal to 1 plus 1 over omega squared. And I can get a common denominator for that if you want, but you don't necessarily have to. But now I'm going to divide both sides by omega plus 3. So once I do that, I'm going to have the Laplace transform of y will be equal to 1 over omega plus 3 plus 1 over omega squared times omega plus 3. And this object, notice that's a cubic denominator. We can do partial fraction decomposition on that, and you'll get something of the form 1 over omega plus 3 plus the PFD of that. So we're going to have an omega squared term. You're going to have an omega plus 3 term. And you're also going to have an omega term as well, since that is a quadratic term. So once you do that, you're going to have what is your numerator constant. So you're going to have 1/3, 1/9, and minus 1/9. And also note that I have a 1 over omega plus 3 and an omega plus 3 term there, and I can combine those two into the same exact entity. So y will be equal to the inverse Laplace transform of, so 1 plus 1/9, that's going to be equal to 10/9 all over omega plus 3. And then we're going to have the inverse Laplace transform of 1/3 omega squared. And then we're going to have the inverse Laplace transform of -1 over 9 omega. Now there are analytical methods to directly evaluate inverse Laplace transforms, but they do require a little bit of complex variables, which we will not get into here. But you should recognize these frequency domain Laplace transforms. That's just an exponential function, that's just a linear function, and that's just a constant. So therefore the solution of our initial value problem, yx, will be equal to 10/9 e to the minus 3x, and then we have 1/3 x minus 1/9. And that is your solution. Obviously, this is very nice for first-order differential equations, but you can also use Laplace transforms for linear, higher-order differential equations as well. And using mathematical induction on the integration by parts approach, like we did for the Laplace transform of the derivative, you should be able to find that the Laplace transform of the nth derivative will be equal to omega to the power of m times the Laplace transform of y minus omega to the m minus 1, y of 0, minus omega to the m minus 2, y prime of 0, and that's going to continue all the way down to omega to the power of 1, y to the n minus second derivative at 0, minus the n minus first derivative at 0. And if you don't like that expanded form, you can always write it in summation notation and write it as the Laplace transform of the nth derivative of y will just be equal to the omega to the power of m times the Laplace transform of y minus the sum from k is equal to 0 to n minus 1. And then we're going to have omega to the power of k times the nth derivative minus k minus 1th order evaluated at 0. And mathematical induction will do quite well with that. And obviously, with this, you can solve higher order linear differential equations. A very basic example you can do is, for example, y double prime plus 5y prime plus 6y is equal to 0. Using Laplace transforms, you should be able to find that the solution to this is actually going to be equal to e to the minus 3x plus e to the minus 2x with a couple generic constants, c1 and c2, in front that depend on your initial conditions, y0 and y prime of 0, that both need to be given in order to give a unique solution. So those are some of the analytical methods and a little bit of theory behind some of the most important things that you should know when going into a first semester differential equations course. Hope you enjoyed this video, and I'll see you in the next one. Take care.